We got a big topic for you tonight here. We're going to tackle this idea of independence. And basically, we're going to throw two events at you. Hypothetically, it could be event A and event B. And the same question we're going to keep bouncing around tonight is, are the two events independent from one another? And before we get into a real formal definition, we've got some different scenarios and questions posed below, and for each one of them, we're going to see if there's a possible connection between the two events. We're going to identify what the two events are and indicate whether or not you think there's a connection. And as long as we've got some kind of reasoning, we're good to go. And you might be sitting there thinking a totally different idea than what I'm going to throw out there, and that's totally fine, as long as we've got some kind of reasoning to back up our thoughts. For part A here, it says, are high school students whose parents or guardians set a midnight curfew less likely to have a traffic violation than students whose parents do not set a curfew? So the two events we're talking about, and we don't always have to use the letters A and B. You really can introduce any letter you want. So for instance, I may use the letter C for having a curfew. And I may use the letter T for traffic violation. And those are the two events that are in play. And what we're doing is we're trying to figure out if they're dependent on one another or independent. And I guess my thought was that my guess is they probably would be dependent on one another. I would expect to see some kind of connection. It doesn't mean that everybody without a curfew has a traffic violation by any means, but I think more or less there probably would be some kind of a theme or connection between the two. Our next one here in B, it says, are left-handed people more likely than right-handed people to be interested in the arts? So our first event would be left-handed people, and our second event would be being interested in the arts. And my first thought was that there would be no connection between those two. I guess I'd be pretty surprised if somebody showed me a study supporting that they were, but I would think there's no connection between which hand you write with and whether or not you're interested in the arts. The next one, though, is pretty interesting here. Are students who listen to classical music more likely to be interested in mathematics than students who don't? Interestingly enough, we'll identify the two events. We've got interested in classical music, and I'll use the letter M for math. And really, like we said, you could use any letter you want. There have been some studies in the past that do a strong link between the part of your brain that processes and solves math problems is also the same part that reads music and processes music and so forth. So I think there is a strong link between those two where they would be dependent on one another. Or we could say not independent anyway. And that's a topic we're going to get into later. D, the last one here. Are people who play video games more than 10 hours per week more likely to select football as their favorite sport? So we've got our video game players. They play more than 10 hours per week. And we've got our football people, not necessarily play football, and that's what's interesting here. They didn't say they're more likely to play football. They just said they're more likely to select football as their favorite sport. And I would guess there is a link between the two because I know one of the more popular video games is Madden Football, and so maybe if they play a lot of Madden Football, they're going to select football as their favorite sport. But again, you might have a total different argument than that, and I'm going to support that as long as you've got some kind of reasoning behind your conclusion. After that brief warm-up here, it's time to get into the nitty-gritty here, and here's our formal definition, and we do have the stars here around this definition because we really want it to pop in your notebook, and we said that two events, A and B, are independent if the probability of event A is equal to the probability of event A given event B. Now that sounds like a lot of mumbo jumbo. Now this last one here, this last thing, event A given event B, that's what we call conditional probability that we just did the previous night. So we're saying, okay, if we already know ahead of time that event B has happened already, now what's the probability of event A happening? Whereas over here in the first one we said, I don't care if event B happened yet or not, we just want to know what's the probability of event A. And if those two probabilities turn out to be equal, we'd say they're independent. And in other words, they're isolated and they really have no influence on one another. Now, how could we summarize this symbolically? All right, and some of this might be slightly new. So basically we're saying if the probability of event A equals the probability of event A given that event B has already happened, okay? Or, now there's another way we could spin this. We could say the probability of event B is equal to the probability of event B given that what's already happened? Yeah, event A. Now the kicker here is that you'll notice, and we could go either way. Both of these are just as good. Neither one's better than the other. But what you really want to focus on here is the fact that if one of these is a condition, okay, this is a conditional one, this one's not, this one has no condition in it, this event has to match the first one over here. Okay, if I flip-flop these two right now, it wouldn't work. Okay, it would violate the rule that we just wrote above. Again, the second option is we've got one that's conditional and one that is not conditional, and this event has to match that event right there, or we'd say all bets are off. A couple of quick little things to get under our belt. We'd say, now referring to the two probabilities we just saw in the back, the probability of event A and the probability of event A given B, we'd say if they're not equal, then we'd say that the two events are not independent. So just summarize, we said if they are equal, the events are independent, and if they're not equal, the events are not independent. Now catch this. This threw me for a little loop. Not independent does not necessarily mean dependent. Believe that, okay? Not independent does not necessarily imply dependence, okay? Which was my first thought. We're going to save that argument for another day, but as far as today goes, that's what we just want to say. We're going to use the terminology not independent, and then we just want to say that doesn't necessarily mean dependence, so I'm not going to use the word dependence at all today, or at least I'm going to try not to. On this slide, we're going to refer back to that symbolic definition that we gave you 2 slides ago, and just to see if we can conclude whether the two events are independent, not independent, or maybe there's not the right information or not enough information that's given. Now what we notice here on the first one, we've got one that's conditional and one that's not conditional, and we've got event A here and event A in the right slot over there. So everything's fitting, and we've got the same probability here and here, and if they are equal, we say that event A and event B are independent. Okay, here's the next one. We've got one that's conditional, one that's not conditional, and again we've got the event K falling in the right slot. However, this time the two probabilities are not equal, therefore the two events, event K and event W, are not independent. Now we got a couple of bear traps coming up for you here. Going to throw you some curveballs. Alright, now here's the problem with number 3, is that both of the probabilities they gave you are both conditionals, and that can't happen. Alright, one of them has to be a non-conditional. And so what we've got here is we don't have the right information, or you can say we don't have enough information to really answer this question. So we're just going to say not enough info. Okay. What we'd have to know in this case is, for instance, based off of this conditional probability, you'd have to know what the probability of just E is without the condition of Q. Or if you were looking at this probability, we'd have to know what the probability of F is without the condition of Q. And if we knew that and it happened to be the same as 0.25, then we'd be cooking and we could say independent. And then for the last one looks so good, but they're messing with us. They're messing with us a little bit. So first you feel good because you got one that's conditional and one that's not conditional, but check out the order here. The G's not falling in the right slot. This has to be a G and this would have to be a B in order for that definition to fit. So I'm going to say again, even though the probabilities were the same, I don't have the right information, or again we'll say not enough information. Okay, so in other words, based off of if I see the probability of G here, I need to know what's the probability of G given B. And if that turned out to be 0.8, again, then we'd be cooking and we could say they're independent. Oh, we got a beautiful story here, nice word problem. And we said the tourism department in New York State surveyed 1,000 random families regarding their vacation plans during the next year, as well as if they watched an online ad promoting New York tourism. And so the table goes as such. For instance, this 300. This represents the number of people that watch the online ad and plan on vacationing in New York within the next year. Or, for instance, maybe you look at the 150. What does the 150 represent? That's the number of families that didn't watch the online ad and are not planning on a vacation in New York State. So forth. So we've seen these two-way frequency tables and so forth, and we're going to just practice interpreting them and tying it into today's new definition of independence. So here we go, part A. What's the probability that a randomly selected family is planning on a vacation within the next year? Now that's a very straightforward probability. There's no conditions in it. And so I'm just going to focus on, let's see, we've got 400 families planning on a vacation, regardless of whether they watch the ad or not, we don't care, out of a grand total of 1,000 families. So I'm saying 400 out of 1,000, or that reduces to, I believe, 2/5, which is about 0.4 or 40%. All right. Part B. What's the probability that a randomly selected family is planning on a vacation within the next year, given, boy, what a special word this is, given that they watch the online ad? When they said it's given, we already know that they watched the online ad. We know that for sure. What that means is we are only allowed to peek in this row right here. We're not allowed to use anything outside of that row. So within that row, let's see, we've got 300 that are planning on a vacation. So I'm thinking 300 out of a grand total 750, and we could reduce that as needed. And by golly, that turns out to be 0.4 also. Holy smokes. Now, here's the kicker. Part C, are the events, let's see, I gotta pick out a nice color here. Okay. Are the events of planning a vacation within the next year and watch an online ad independent? Well, if they are, here's what's got to happen. There's really two ways we could do this. Number one, let's do the probability of vacation, and we have to ask ourselves, is that equal to the probability of vacation given that they watch the ad? And I'll use the letter A for ad. And those are the two things we just already figured out. In part A, we figured out that the probability of vacation is 0.4. In part B, we said the probability of going on vacation given that they'd seen the ad was also 0.4. And because they're equal to each other, we'd say that these two events are independent. Yeah. Now, I mentioned there's two options. Okay. The second option here, and you get the same conclusion, is you kind of turn around and you say, okay, what's the probability that they watch the ad? And then what's the probability that they watch the ad given that they are going on vacation within the next year? And you'd get the same thing. You'd get not necessarily 0.4, but you'd get the same number here as you do over here, and you'd come to the same conclusion that the two events are independent. All right, let's see if we can fire up another example using the same scenario and the same frequency table. So first of all, what's the probability that a randomly selected family did not watch the online ad? So we're looking at what's the probability of not watching the ad. So I'm going to use N for not, A for ad. And there's no conditional probability in this case. It's just straight up how many people did not watch the ad. And I said there's a grand total of 250, regardless of whether they're planning on going on vacation within the next year or not. We don't care. And that would be 250 out of 1,000. And as we reduce that, it turns out to be 0.25 or 25%. Nice cool number to work with. Part B, what's the probability that a randomly selected family did not watch the online ad given, so here's our condition, given that they are planning on a vacation within the next year? And what this does is this limits us to what part of the table we're allowed to look at. So we already know that we're 100% sure that they're planning on a vacation next year. So we're locked into this column right here. And we have to stay within this column. We're not allowed to look anywhere else. And we're saying within that column, what's the probability that they did not watch the online ad? And I'd say that's 100 out of 400. So the probability that they did not watch the ad given that they're going on vacation is 100 out of 400, which again reduces to a nice cool 0.25. And that's going to set us up for this next question. They want to know if these two events, the event of going on vacation and not watching the ad, are independent from one another. And so basically what we're saying is we know that the probability of not watching the ad is equal to the probability of not watching the ad given that we're going on vacation. And because those are equal to each other, we'd say the two events are independent. Okay, a little different scenario here. It says 50 adults were surveyed regarding what they like to do during their leisure time. So we've got, of the men, 2 of them like to dance, 10 like to play sports, and 8 of them watch TV. Out of the women, 16 like to dance, 6 like to play sports, and 8 watch TV. And you can see all the totals around the outside of that table. So our question here is, are the events of liking to play sports and men independent, or conversely not independent? And there's, like I said, there's more than one way to do this. I'll randomly pick one of them, and then at the end I'll introduce you to the other option, and maybe that's the one you did. And I'll tell you what, I think we've maybe done enough that maybe you can hit the pause button and try this one yourself. And I tell you, if you get this one right now by yourself, you ought to give yourself a big pat on the back, and you're in great shape, because this is really all we're going to hit tonight. So here's what I'm thinking. I'm going to say, okay, what's the probability that they choose to play sports during their leisure time? And is that equal to the probability of playing sports given that they're male? Okay, so that's the question. I'll put a little question mark here. Are they equal? Because I don't know if they really are yet or not. We're going to find out. Okay, the first one, probability of playing sports, is I'm going to say there's 16 total people out of 50. Now, this other conditional, they said the condition is we already know that we've chosen a male, so we've got to lock ourselves into this row right here, and sports would be 10 out of 20. And we could turn those into fractions just to confirm it, but I'm going to tell you what, these bears are not equal. They are not equal. Therefore, we'd say these two events are not independent. Okay, simply because these are not equal to each other. Now, the other option we said that you could have gone with, and maybe you did do this, we'd say, what's the probability that we choose a male, okay? And is that equal to the probability of choosing a male given that we know they like sports? Okay? And again, that's a question mark. And the key here is, you notice this event here has to match that event right there. And if those two events don't match each other, then we haven't followed the definition that we introduced the topic with. And we could carry it out, and again, we'd get two fractions that are not equivalent, and therefore the events are not independent. All right, I think as we come down the home stretch, I think we're in a position here where you can try this one on your own. It's same concept as what we've been doing, of course. I don't think there's any real major new wrinkles, but I'd encourage you to hit the pause button here and try this one totally on your own and see if we're on the same page. So as I dissect this problem, what I notice here in the first sentence is that they said the probability that a random student does have a job during the school year, I'll use J for has a job, is 30%. Now they said there's two events here. We'll use the letter J for job, okay, and I'm going to use the letter E for being in 11th grade. So those are the two events here. And they said that having a job and being in 11th grade is not independent. All right. So, and that's ultimately, we'd say that the probability of having a job is not equal to the probability of having a job given that they're in 11th grade. And the reason I know they're not equal is because they just told me the two events are not independent. So basically what we know is that if this one's 30%, this one over here is going to be anything but 30%. It could be 29%. It could be 50%. It could be 74%. It just can't be. It's anything other than 30%. So I'm going to say not equal to 30%. That's the one thing I know for sure. Okay, another great question to try on your own and see how you would attack this by yourself. And the question is, for this group of students, does the data suggest that gender and preferred music style are independent from each other? And so really they didn't specify which gender, they didn't specify which music style. So really you've got the freedom to pick either of the genders and any of the three music styles they threw in the table. And basically if you can just prove that one combination is not independent, then you're really proving that they're all not independent. So we just need to find one group here. And I'm probably just going to jump on the first one that I see here in the table. So we're going to start with, I'm going to use T for techno and F for female. And I'm going to try to prove that female and techno are not independent of each other. In order to do that, I'm going to say, okay, is the probability of randomly selecting a female equal to the probability of selecting a female given that we know they like techno music? All right. So let's start with the non-conditional. The probability of choosing a female would be, and you notice we don't have the totals here, so I'm going to work my way around the table here and see if I can create the totals. We'll say total here, we'll say total right here, and we're going to go ahead and do a lot of adding. Probably double check some of my adding here to see if you got the same. I had 106 female students total out of the 200. So the probability of randomly choosing a female student would be 106 divided by 200. Now the question is that equal? And I'd like to put a question mark because I'm not sure if they're equal or not. What's the probability of selecting a female given that we already know ahead of time that they like techno music? So what I'm going to do is I'm going to lock myself in this column right here, and I'm going to say there's 54 females out of 90. So there's my probability. And now the question is, are these fractions equivalent? So I'm going to turn them both into decimals just to confirm whether or not they're equivalent. And what you'll notice, the probability of choosing a female was 53%, and the probability of choosing a female that, given we know they like techno music, was 60%. And since they're not equal, we say the two events are not independent. And therefore, like we said, if we can find one combination that's not independent, then that carries over to all the genders and all the preferred music styles. So I hope you're in good shape tonight. We'll get some more great practice in tomorrow, and before you know it, we'll be nailing this one on the test. Good luck.